Okay, so let's continue on to the next example. Today I want to explore again a little bit more about matrix multiplication with the Tenstorrent hardware. Oh, first of all, I did move my wormhole to another computer, not on my main workstation, which I'm looking at right now, mainly because it was way too loud, and so I built a new PC, not too expensive, just to have that sitting under a desk in the other side of the room, so that I could tolerate the fan noise a little bit more. It's helped a lot. As you can like hear from things, it's not as bad as before. So yeah, hopefully that'll be better. And also, it is on a lower end machine in that the CPU is a i7-13700, and so it lacks a lot of the capabilities and hardware acceleration that you would normally find in like higher end like server CPUs like Xeons, where it has like things like AMX and AVX 512 and all these other CPU extensions that kind of make the wormhole not, I wouldn't say useless, but it's hard to appreciate what the wormhole can do with hardware that's that high end, because the amount of floating point operations per second, especially with bfloat 16, it's kind of like creeping to that level that the wormhole can do. So then it's hard to go like, what's the point, right? So by putting it into another machine, especially a machine that's more mainstream, I can actually demonstrate down the line the benefits of the wormhole, and why hardware such as what Tenstorrent is trying to do actually makes sense from a cost, power efficiency perspective, and also just the sustainability aspect of it. Anyway, enough of that. I just want to let everyone know that that hardware's moved. So going forward, in the next videos, I'm working remotely off of from my main workstation into the real machine that the wormhole's in. Small details, but it explains a lot of like why you would see like things like SSH and things like that here. Okay, going back to the real point, I want to explore matrix multiplication a little bit more. I know you're probably sick and tired of seeing that by now, the matmul thing, but it's important because it helped me understand how to move things between the CPU memory to the wormhole memory. And so the goal today is to convince ourselves that ttnn.matmul can only run on the device, like could really only run on the wormhole, and the the matrices have to be two-dimensional at least. They have to be in tile layout, and it helps that it's in bfloat 16. That third one isn't a hard requirement, but it helps us understand that we can take advantage of specific types of acceleration if we are in bfloat 16 rather than regular floating point. So I'm just going to first of all save this notebook to here. So I'll put it in notebooks, and I'll call it 04 matmul example, or matmul behavior. Okay, matmul behavior. So let's save that notebook, and let's actually quickly just write those notes down, right? So matmul behavior. So goal of this notebook is to convince ourselves that a matmul can only run on a device, Tenstorrent device, if the inputs are one, at least two-dimensional tensors, and then two, the tensors are in tile layout, and then three, not hard requirement, The tensors are in bfloat16 format. Precision or data type. Okay. So yeah. Ooh, what's going on? Uh-oh. Did I accidentally turn on something? Oh, there we go. bfloat16 data type. Okay. So yeah, that's what we're going to be looking at today. So like first, we're going to demonstrate that matmul won't work when we attempt to multiply two tensors in row major layout, which is like the second type of layout that Tenstorrent supports. So if we go to Tenstorrent tensor layout, let's go here, tensor layout, not this one. Wow, let's just go here, layout. Yeah, tensor layout. So if we go right here, so remember that row major is like a zigzag motion, right, to represent a tensor, and this is like probably more intuitive a way to think about it, right? So like we know that if we take the first row, every single element is sequential like an array, but then the second row, if we kind of take this 2D tensor and kind of flatten it out into a 1D array, it does make sense in that the first element of the second row, for example, continues off from the last element from the first row, the last column. And so that's what row major layout is. But unfortunately, when we do device operations, we want to take advantage. We can't use row major layout. That's like the unfortunate thing, because we have to shift our mind to a different layout, and that's tile layout. And tile layout apparently is more natural for the hardware itself to start doing compute on, because you can actually take these blocks of like subtensors, I guess you can call it that, and kind of shard it out to different cores in the Tenstorrent hardware itself. So tile layout is where we want to be when we do the compute. So we do a matmul. We want to have our tensors be in tile layout in this case. And so we can read that right here. So in tile layout, the elements themselves are placed within a 32 by 32 square called a tile, right? So minimally, a tensor that is represented as tile layout has to be a 32 by 32 tensor. And there are helpers. There's API to help with that if it's less. So basically, the tiles themselves are then still stored in a row major order. So inside those tiles, right, they're actually in row major order. Kind of confusing, right? It's like you take the big tensor, you represent them as tiles, but then inside those tiles, they're in row major, right? And then if you take a tile to a tile, like this one right here, right? Notice how it's itself in row major, like the bigger subtiles make up a row major layout for the overall tile. So in order to transition to tile layout, this helper, right, ttnn.matmul can be used. When the height or width of the tensor are not divisible by 32, padding is automatically provided, right? So if you're not 32 by 32 or 64 by 64 or 128 by 128, if it's like anything that's less or in between, ttnn.matmul is going to help by padding that tensor so that you get an automatic, like, nice workspace for the hardware to deal with, right? So yeah, that's tile layout. So yeah, let's show why row major layout doesn't work. So to set ourselves up, we do need to enable tracing so that we can see how these tensors are flowing in and out of hardware. So we can do import OS. Remember, we had to set up our let's actually turn this into code. Okay, so we had to set up our environment variables. Got to set up the kernel. Okay, so the environment variable that we need to turn on tracing is ttnn config overrides. Okay, and again, it takes that JSON, so I'm going to type that out like manually. Okay, so that's the JSON key, that's the value, and then that's going to be false for sure. Okay, so it's going to be called enable fast runtime mode. Okay, so that's the environment variable that we need to set correctly. Okay, then we need to get our dependencies, right? And so the dependencies, they're just going to be torch and ttnn, and then the tracer from the ttnn. So we could do import torch, import ttnn, and then from ttnn.tracer import visualize and trace. Those are the two things that we need, or yeah, two things we need from tracer. But overall, we need the torch and the ttnn library. So let's just annotate so I don't have to go through that later. So set up environment, right? First, set up the environment for tracing by configuring the ttnn config overrides environment variable. Okay, next, import required libraries. You need torch, ttnn, and tracer related modules. Okay, so let's just make this a heading 2. Okay, what was this one? How come heading 2 it looks the same size to me? Oh well. Okay, I'm not convinced. Why? Okay, whatever. Okay, so does this work? Does this work? There we go. Okay, I was expecting to see something like the hardware kind of initializing, but we'll see. All right, anyway, so a lot of operations for ttnn like matmul is going to require a device handle, right? So I like to just grab the device handle early on. So we can just say grab device handle. So basically we need to set up the device. So device ID is going to be 0, why 0? Because that's the only device that we have. Again, I like to just do repetition here. So if we go to, or let's activate our virtual environment for TTSMI, but we do TTSMI, no Tensor. Oh, of course, I'm not SSH'd. Give me a moment. Okay, let's see. Now I'm SSH'd into Tensor. I forgot I moved. See, I got tricked, right? I moved the card to another computer. I forgot that's no longer in this computer. So ttbnb bin activates TTSMI. All right, so this computer here, it has the device at 0. So that's what the ID corresponds to, right? So the ID of your Tenstorrent hardware. So now if we know that ID, we can just grab the handle with ttnn open device with the device ID. Okay, and that detects the chip just fine. If again, if you see this log, it's all is well so far. Okay, next we want to create some input tensors just to mess around with. So let's see, let's turn this to markdown. Okay, create input tensors. Okay, we'll create and trace 2 input tensors to be used to demonstrate the operations. First, we want to show that the input tensors are in row major layout. Okay, so we're going to create tensors that are in row major layout first. So to begin doing that, we need to wrap our tensor creation, right, with the with trace block. So with trace, turn that into code, by the way. Okay, with trace, we're going to create an input tensor A, and we're going to convert a torch tensor to a ttnn tensor. So to do that, we just use ttnn from torch, okay, and then we'll pass in as the argument a random torch tensor of shape 5 by 5. Let's say that. So torch rand n 5 by 5, and d type is going to be ttnn.bfloat16. Now by default, these tensors are going to be row major layout. So and I'll demonstrate that to how we would know that, right? So we'll create another random tensor, same thing, from torch. So basically pass in that torch tensor. From torch, we'll turn that into a ttnn tensor from that original torch tensor. So yeah, create a 5 by 5 one. D type is going to be bfloat16 again. And then what we can do is we can visualize. Okay, so visualize A, visualize B. Okay. What is it? Do we have it? Oh, Graphics is not installed on this. Yeah, different computer again. So easy enough. Go in here, sudo apt install graphviz. Oh. Okay, so let's install graphviz real quick. All right, let's try that again. So, okay, so here we created a random torch tensor that's 5 by 5. Originally, it's going to be float 32, but then we're going to pass that in as an argument to ttnn from torch. Okay, and what comes out of it is going to be a ttnn tensor that's of shape 5 by 5, bfloat16 data type. But important thing to know here is that it is row major layout, and I realized that this may be too small, so let me zoom that in a little bit so everyone can see. So right here, right, row major layout. Same thing for tensor B. So we created tensor B originally as a torch tensor with float 32. Then we call ttnn from torch with that as input. Out comes a ttnn tensor that is bfloat16 data type with its layout being row major. Okay, so far so good. Okay, I actually wonder if we do like, given that with trace kind of just traces everything, if we just visualized A, does that even work? Yes, it works too. Weird. So we get both A and B. Sorry, this is my realization is that visualize will always output everything in that trace block. I wonder if I can quickly look at the API just to get a clarification. Visualize tracing ttnn operations. Yeah, we were here before, but I didn't read in thorough. So there is no oh, I think we only need to trace the final thing, I guess. Okay, so tracing looks like it'll just capture everything, and then you just need to specify tracing on the output, the final thing. So makes sense. So we could do visualize A and visualize B because those two are outputs technically. Okay, sure. Okay, so next thing we want to do is we want to send these tensors to the device. So we do with trace again. We want to see that happening. So A is going to be sent to the device. Okay, what device do we want to, what tensor do we want to send? A, and then the device handle, same thing with B. So now after this, both tensors should be in the device. Okay. And now, so again, we're building up that graph, right? Let me see if I can blow this up. Yeah, so we're building up this graph, and you can see here that we created the, actually, I can just zoom in like this. Okay, so we built out the tensors again, like before. Those become ttnn tensors. And then we send them to the device with the toDevice method. And as input, those are ttnn tensors, but in row major layout still, right? Now in the device, they are still in row major layout. They're sitting in there the same way we pass them in, except that where is it sitting inside the device? Well, it's in DRAM. Okay, it's in that GDDR6 memory inside that wormhole card. So same thing with B. Okay, so it's the same thing. Okay, so now we have two tensors that are inside the device. Okay, so next, let's actually attempt. So let's annotate again. Create input tensors, then we'll send them to the device. Okay, send the tensors to the device. Okay, next. Oh, okay. Next, so at this point, the tensors A and B are in device storage, DRAM, right? Device GDDR6 RAM. GDDR6 RAM, there we go. And in bfloat16. Most importantly, both tensors are also in row major layout. Okay? So the next thing we want to do is we will now attempt to perform a matmul on these tensors. And let's see what happens. Okay? So now let's attempt to do that. So let's create a matrix C, for example, and we're still going to trace that. Okay, we're going to attempt to trace it at least, but we'll find something interesting that happens. So with trace, C is equal to ttnn.matmul, and that takes in two tensors, A and B. Okay, and we're going to see what happens here. First, visualize C. And then what we want is, let's print C. Okay, so now we get an error. What is the error? So C, the error happens in C equals ttnn.matmul. And if we kind of expand this error and scroll up, we do see this error here that says inputs to matmul must be tilized, right? So it's saying that matmul has to be in tile format. So if we go to the API here again in the documentation and we read carefully about matmul, it says right here very clearly that the input tensors need to be tiled and at least one-dimensional. So you're gonna start seeing that a lot in the API. So especially we go to like binary operations like adding and multiplying. Like let's take multiply, or let's take something different. Let's take divide, right? You'll find that what's expected right here is that the layouts have to be tiled, has to be in bfloat16. Okay, so like a lot of these operations on the device will require tensors to be in this format. So that's what we have discovered just now. Now, when we get errors like this, and we have a device open still. We still have the device handle open, but we have to have an exception. One thing I recommend always doing is that you should always close the device and open it again. Okay, so let's add some annotation here is that, okay, an exception occurred because our tensors are not in the proper tile layout. It crashed. So let's clean up by closing the device and then opening again. Okay, so since we had an error that happened, we don't want that device to be hanging, so we can just do ttnn.close device and then specify the handle, which was device. Okay, so now we're in a good state again. Okay. Oh, and we also have to close tracing. So we also have to close tracing. Close or disable tracing. Disable tracing too. Okay. ttnn.tracer.disable tracing. Okay. Right. So let's get back to a decent state. So now let's do operating in tile layout. So now we will explore multiplying tensors in tile layout. And this is the expected layout for operations like matmul performed on the device. So this is what we've been working for, right? Working with whatever. Okay. So, again, we're gonna have to create tensors A and B, send them to the device, and then we're gonna operate on them. Now, let's just do that all in one trace block, just for like to simplify, right? So let's do with trace again, and let's create tensor A, ttnn.from torch, okay, and let's create a torch tensor. So torch.randn with a shape of 5, 5, d type, ttnn.bfloat16, okay, and then let's create the layout right away. So let's tilize it right away. So we're going to create a ttnn tensor that's immediately tile layout instead of the default row major layout. So you'll understand now that actually we don't provide the layout as an argument when we do from torch. What we actually get out is a tensor that is row major by default until we override that with the tile layout. So we'll do the same thing with B. This is repetitive typing, but it helps us learn the API. Okay. So now I have these two tensors created. Next, we want to send them to the device. So what happens is that we have two ways to do this. We can manually send them to the device using toDevice, or when we create these tensors, we can actually specify the device right away. But in order to specify the device right away, or even send the device, we need to actually grab a handle to that device. So again, just like before, we need to open the device for the device ID that we want to grab the handle to. So in this case, I'll specify device ID equals 0 again, and then I'll open. So I'll open and grab the handle. Can't type. Okay, so we've grabbed the device's handle, and then just for making sure that we don't forget to close the device, we'll just close it right here at the very end. Okay. Okay. So we can directly create those tensors and just send them to the device with one shot. So that is actually going to be the device keyword param here, or keyword arg, if that's what you want to call it. So that's also another way. Instead of just creating these tensors and calling toDevice to send the tensors to the device, we can create them on the device with this from torch API call. So in this case now, if we visualize A, visualize B, okay, maybe I don't want to close the device right away. You know what? Let's split this code. Let's let's add code here to open the device. Okay. And then let's actually add code down here to close the device. Okay. Okay. So let's open the device. I'm not sure why that's taking long. I actually hear the device like in the background. It's like struggling for whatever reason. I don't know what's just going on. It's working. Oh, okay, there we go. No idea what happened. Anyway, so let's see. So there is an error. Is there an error? Let's see. An op tensor to device. What happened? What happened here? With trace, did I visualize? Is this supposed to be outside the block? Let's see. Let's learn something new. Oh, it's supposed to be outside the block, I guess. Anyway, yeah. So executing that, we created two tensors again, like before, but now look at what happens. So we created torch tensors, random shape 5, 5. Okay, same thing with the B side. Then we call from torch with that torch tensor in float32 format as input. But what comes out is a ttnn tensor that is again 5 by 5 shape, bfloat16 data type, already tiled and also sitting in device memory already directly just by one API call, right? So yeah, a convenient way to do it. So you don't always have to do like the whole to layout then to device type of thing. If you know that you want a tensor created exactly with tile layout and already on the device, you can just use keyword arguments like this here, and this works with from torch. Okay. Next, let's add code below here because we don't want to close the device right away. Let's actually now do the same thing. Let's do a matmul. Okay, so with trace c equals ttnn.matmul ab. Okay, and then now let's visualize c. And this is interesting, right? So easy. It's just basically a regular matmul, but this time it worked because again we fit the requirements. We were in tile layout and the tensors were in the device already. Okay. So yeah, we'll see here that again this at this point these earlier steps are obvious, but you want to send them to matmul right here, this function called matmul, right? And then pass them as inputs. Okay, input 0 and input 1, both in DRAM, outcomes a result that is in bfloat16 tile layout and also still sitting in device memory. So if we go and look at what C is, okay, we'll see that it is a tensor that is a 5 by 5. Okay. At this point, still in device, but let's say we want to move it back to the CPU. Okay, so CPU, or let's just keep it as C. Okay, let's just keep it as C. We can do okay, let's keep it as C, but let's move that tensor from hardware back to CPU. So it's going to be called ttnn from device. That's the API we want. Now, looking at the API from device, ttnn from device will take in just the input tensor, so the tensor on the device. it will magically know which device it's sitting in for whatever reason. I don't care. It just works. So then we can just do ttnn from device, tensor on device. You'll get back a ttnn tensor, but now it's going to be back on the CPU. So ttnn from device, C, and let's visualize C again. And let's actually add markdown here. Say let's move the tensor back to from hardware, from Tenstorrent hardware back to the CPU. Still, this tensor will still be a ttnn tensor. So it's important to remember that it's still ttnn tensor, okay? So I'm going to call it C equals ttnn dot from device with C as the argument, reassign it back to C. And then you'll see here again, slowly, that if we look at the operations that occurred, so this matmul resulted in an output tensor that is, again, the requirements that we need, basically a 5x5 bfloat 16 tile layout tensor living in GDDR6 memory. We'll then call from device to move this input tensor sitting in the device, outcoming another ttn tensor, now no longer in the device because it doesn't say memory here. It doesn't have that memory here. So we're back in the CPU. We're back in CPU land. Okay. So now we have that ttnn tensor. So let's say now we want to do something with that. Let's say we for some reason we want to use torch again. So with trace, so trace actually can trace torch operations. If you haven't noticed yet from these two up here, we could do ttnn to torch. I think it's called to torch. So we look at the API again. We can do to torch. To torch takes in what? A tensor. Okay. So the rest of these should be optional. So we can just do to torch with the tensor, and it will just return back a torch tensor. And let's see what happens then. So C equals to ttnn dot to torch C, and it will visualize C. Okay, so let's add some markdown. Say let's convert the ttnn tensor back to a torch tensor. Okay, so that's output. And looking closer, okay, so after we've moved the tensor from the device back to CPU memory, we call toTorch to turn this ttnn tensor in tile layout back to a torch tensor that is of size 5x5, but now it stays as bfloat 16. It doesn't change the data type, right? It just stays as bfloat 16, and then now the layout becomes strided. So now it's back to the native memory layout that torch expects. Okay, so we know that we can't matmul on row major tensors, but can we matmul on tensors on CPU, right? What would that give us? We know it has to be on a device, but what kind of error will we get? So let's close the device and let's start a new one. Let's start a new block, right? So let's do this. Attempt to matmul on tensors not in hardware, Tenstorrent hardware. Let's see what kind of error we would get if we attempt. We get. If we attempt to matmul on tensors not on the device, but still living in CPU. Okay. So with trace again, A is going to be a tensor. So from torch. Okay. So let's do this. Let's right away create a random torch tensor, 5x5, D type. Right away ttnn.bfloat 16. Layout is going to be ttnn.tile layout. And then we're going to keep that on CPU memory. So B is going to be the same thing from torch.randn 5x5 dtype ttnn.bfloat16. Layout is going to be tile layout again. Okay, so at this point we have created tensors. Let me just visualize that. So at this point, we create tensors that are still sitting in CPU memory. So we're back to where we were in the beginning, except that now instead of row major that we've created right away, we've done the whole tiling. So now let's attempt to matmul. So attempt to matmul. Okay, so let's say we didn't know the fact that matmul requires tensors to be on the device. Okay, so it's going to be straightforward with C equals matmul AV. And let's visualize if we can even make it, but we can't make it because we have an exception here that's thrown right away, and the error that we get, we clicked on the scroll, enable scroll, whatever it's called. It says cannot get the device from a tensor with host storage. What does that even mean? Cannot get the device from a tensor with host storage. It means that the tensor is on host storage, so we haven't found a device that's bounded to that tensor. Okay, so we can't really operate on it with matmul. So that's the type of error that you would get if you attempt to perform a tensor operation on tensors that aren't living in a device but requires them to be living on a device. So yeah, okay. I think that's it. Yeah, so as far as like tilizing goes, there's like other ways to tilize things. There's like tilize with padding, meaning that you can specify, like let's say you had tensors that were like they're not 32 by 32 divisible, and you want to add padding. You can actually add padding manually if you really want to control that. I think it's called tilize with val padding. Yeah, tilize with val padding. Like you have these types of helpers that, you know, if you use it correctly, you can tilize in very custom ways. I don't know. I feel like that's more complicated. I don't see myself using that yet. I don't think I'm skilled enough yet. So I'm just gonna use either creating directly as a tensor I'm going to create a tensor directly as tile layout, or I'm just going to use toLayout. I could see that though, like this would be useful. I mean, like you can control the value that you pad with, right? Because I think with toLayout, where that padding occurs, let's find toLayout. toLayout. So like with toLayout, I think the padding is some sort of special value, some large value that is used. I'm not sure. I don't know. Anyway. Yep. I think that's it for today. I mean, that's what I wanted to show, that why it matters to be on a device when you're performing matrix multiplication. So let's do this. Let's first of all, we need to ignore this folder here. It wants to add it, so let's fix that. Ignore .ttnn star. I guess this takes a while to refresh. I don't know. It looks like we're only committing 2 things, so let's just commit. Commit m matmul behavior. Okay. All right. I think that's it. Thank you, everybody.